this video, we are going to talk about the reaction of aldehydes and ketones. So the reaction of aldehydes and ketones normally follow a general rule. So what happens is that, for example, if we have an aldehyde, the first thing is that there is first a nucleophilic addition, and then the second part is an acidic workup. So if you add these two to an aldehyde or a ketone, what will happen is we are going to get this product. So this is the product we are going to get. So let's take a reaction and use it to demonstrate this. So for example, let's assume that we have ethanol and then we add water to ethanol. The product we are going to get is this is the product we are going to get. We are going to get a germinal diol. So let us use reaction mechanism to show how we are going to move from this to this germinal diol. So the first thing is that we have this as starting material, which is the ethanol. But we know that water has lone pairs of electrons, actually 2 lone pairs. But if we consider this molecule, this oxygen atom is more electronegative than this carbonyl center. And therefore, these electrons that are shared between the oxygen and the carbon are more pulled towards the oxygen than the carbon, making the carbon center electrophilic. So this nucleophile will donate one of its lone pairs of electrons to this carbonyl center, causing the pi bonds here to break. So when this happens, it will lead us to this intermediate. So because the oxygen donated one of its lone pairs, it becomes positive. It will assume a positive formal charge. And then this was a proton that already was on the molecule. But we know that this is a nucleophile. So what will happen is that it will use its lone pairs to pick one proton, causing these electrons to be moved here. So in the last step, we are going to get our final product, which is this product. So this is what leads, this is the reaction mechanism that will lead us to the final product. So the first reaction of an aldehyde and a ketone that we are going to talk about will be the addition of the Grignard reagent. Now, a Grignard reagent is a magnesium atom that is sandwiched between a hydrocarbon and a halogen, where X is either a chlorine, a bromine, or an iodine. So let's take an example. Let's assume we have ethanol and we have this Grignard reagent. That's the first step. And then the second step, we have H3O plus in solution. What will be the final product that we are going to get? What will happen is that this hydrocarbon will become attached to this aldehyde. So this is the final product that we are going to get. So there is a CH3 here, and then there is a proton that is going to be here. So now let's use reaction mechanism to demonstrate this. So we have the ethanol here, and this is our Grignard reagent. Now, the electronegativity of carbon is 2.55, and the electronegativity of magnesium is 1.31. So if we check these two values, you see that the electronegativity of carbon is far, far greater than the electronegativity of magnesium. What it means is that the electrons that are in this bond are more pulled towards the carbon than the magnesium, and therefore the carbon is more nucleophilic than this magnesium. So what will happen is that in the first step, this will donate these electrons into this carbon center, moving these pi bonds to the oxygen. So this is the intermediate we are going to form in solution. So we are going to get, this is a proton, and then this is the CH3. So in the next step, remember that we have hydronium ions in solution. So we have these hydronium ions in solution. So what will happen is that this nucleophile will pick one of the protons, causing this bond to be moved to the oxygen. So the final step is going to give us our final product, which is this product. So let's assume that we are given this reaction. What will be the product? So you see that this is cyclopentane carbaldehyde, and we are adding a Grignard reagent. So just as we did previously, this is the product that we are going to get. So there is going to be an alcohol at this part. Then this is the original proton from the reaction. This part is going to be here. So this is the product we are going to get. So let's use reaction mechanism to show how this product is going to form in solution. So what will happen is that this is our cyclopentane carbaldehyde. Then this is our Grignard reagent. So this bond is going to break to attack this carbonyl center, causing these pi electrons to be moved to the oxygen. So in the next step, this is what we are going to form in solution. Then remember that we have H3O plus in solution. So this is our hydronium ion. So what will happen is that this nucleophile will pick one of the protons, causing those electrons to be moved to the oxygen. So in the next step, we are going to form our final product, which is this product. So let's consider this reaction. In this reaction, we are supposed to work backwards. We have been given the final product, and then we are supposed to determine the starting material. So you see that this portion is the part coming from the Grignard reagent. If you look at this Grignard reagent, it's a cyclopropane attached to MgBr. So this is the part coming from the Grignard reagent. So if we remove that part, and you can see that always we form, the molecule has an OH. So for example, if I extend this and put the OH here, so these bonds will be broken and then move to this carbon center. So we are going to remove this H, and then that is where the aldehyde is going to be, and this is just a base. So in the end, this is the product, the starting material from which this product was gotten from. So this is our starting material. Now let's use reaction mechanism to show this. So first, this is what we start with. This is the product that we are given. So this is the product that we're given. So what will happen is that this will be moved to this. These electrons will be moved there. And when it is moved there, it will cause this to break off. So when it breaks off, in solution, we are going to form this. So this is what we are going to form in solution. And then finally, remember that we have water molecules in solution. So the water will use one of its lone pairs to pick this proton. And when it picks this proton, it will cause these electrons to be moved here. And therefore, we are going to get our final product, which is the starting material. The next reaction we are going to talk about is the addition of an organolithium. And that one also follows just like the addition of a Grignard reagent. So for example, let's assume we are given this aldehyde, this ketone. And then a methyl lithium. In the second part of the reaction, we are given a hydronium ion. So what will be the product? What will happen is that we are going to get just what we did previously. So in this case, this part will be the nucleophile, so it will get attached to the ketone. So this is the product we are going to get in solution. So this is the part coming from the organolithium. This is the methyl that was already in solution. So this is the final product we are going to get. Now let's use reaction mechanism to show it. So what happens is that this is our starting material. Then we have methyl lithium. The electronegativity of carbon is 2.55 and the electronegativity of lithium is 0.98. So if you check these two values, you see that carbon is more electronegative than lithium. And for that matter, carbon, these electrons are more pulled towards the carbon than the lithium. So what will happen is that in the first step, this will donate its lone pairs into that carbonyl center, causing these pi bonds to break. So in the second step, we are going to get this intermediate in solution. Then this is the CH3. But remember that we have a proton in solution. So this is the hydronium ions. So what will happen is that this oxygen will use its electrons to pick this proton, and therefore we'll get the final product in solution, which is this product. Let's consider this question. What will be the final product? So what will happen is that this nucleophile will be moved to this carbon center, and then there will be an OH on top. So this is the final product we are going to form. So there's always the OH here, and then this is CH2CH3, and then so this is the product we are going to form in solution. Then because of this H here, we will form lithium chloride as well. So let's use reaction mechanism to demonstrate this. So the first part of the reaction, this is the organolithium. So these electrons are pulled towards this carbon than this lithium, and therefore this will break, causing these pi bonds to be moved to this oxygen. So we are going to form this intermediate in solution. But remember that we have HCl in solution. So what it means is that we have free protons there. So this proton will be picked up by this oxygen we use is lone pairs to pick up this proton, so we can get the final product. So all the reactions follows the same mechanism. It doesn't change. So immediately you understand the mechanism, you can do all the reactions. The next reaction we are going to talk about is the addition of the sodium borohydride. So for example, let's assume we are given this starting material, which is cyclohexane carbaldehyde, and we are supposed to add, the first part is we'll put sodium borohydride, and then the next step is the acidic workup H3O plus. What will be the product that will form? So this is the product that will form. Always we'll form our OH and then we'll add the nucleophile, but in this case the nucleophile will be a proton. So this is the product that will be formed in solution. So let's look at the reaction mechanism that will take us to this product. So let's start with our starting material, cyclohexane carbaldehyde. And then in solution, sodium borohydride will exist in this form. So this will have a negative formal charge. Now, the electronegativity value of a proton is 2.2, and that of boron is 2.04. So you see that a proton is more electronegative than boron, and therefore the proton will act as the nucleophile. So these electrons will be moved to this carbonyl center, causing these pi bonds to break. So in the intermediate step, we are going to form this in solution. So this is the proton coming from the sodium borohydride. And then remember that we have H3O plus in solution. So what will happen is that this one will use one of its lone pairs to pick a proton, causing these electrons to be moved to the oxygen here. So we are going to get our final product, which is this product. So this is a reduction reaction. The next reaction we are going to talk about is reduction of an aldehyde or ketone with lithium aluminium hydride. Now the difference between lithium aluminium hydride and sodium borohydride is that lithium aluminium hydride is more strong than sodium borohydride. So lithium aluminium hydride will reduce both esters and carboxylic acids, but sodium borohydride will only reduce aldehydes and ketones and not esters and carboxylic acids. So we are given this starting material. The presence of a lithium aluminium hydride and a hydronium ion. So this is what we are going to form in solution. So we'll form our OH here. There will be a proton here and there will be another proton here. So let's use reaction mechanism to show this. So in solution, this is how lithium aluminium hydride will exist. Now, This proton is more electronegative than this aluminium. So these electrons are going to be moved to this carbon center, causing the pi bonds to break and be moved to the oxygen. So in the next step, this is the intermediate we are going to get in solution. But remember that we have H3O plus in solution. So we are going to, this one will pick one of the protons and cause these electrons to be moved to this oxygen. So in the final step, this is what we are going to get. So we are given this starting material, this ketone. And the first step, we'll add sodium cyanide and then the acidic workup. So it's the same thing. Always and always, it doesn't change. The mechanism will always lead to this product that has an OH here. And then the nucleophile, cyanide is added to it. Always and always, that is what the kind of product you get. So let's use reaction mechanism to demonstrate it. So in solution, this is how the cyanide will exist. So the cyanide is the nucleophile. So this nucleophile will donate its lone pairs to this carbon, causing these pi bonds to break. So in the intermediate step, we are going to get this intermediate in solution. But there is H3O plus in solution. So the final step, which is the acidic workup, this will use these lone pairs to pick this proton, causing these electrons to be moved to the oxygen. So in the final step, we are going to get this product. So this is how to add a cyanide ion to either an aldehyde or a ketone. The next reaction we are going to talk about is the addition of the hydroxide ion. So we are given this starting material. And then the first step is to add sodium hydroxide. The second step is the acidic workup. So this reaction is like the first one we did when we added water. We are going to get a geminal diol in solution. So this is the product we are going to get. Let's show it by reaction mechanism. So in solution, the sodium hydroxide will exist as an OH minus ion and sodium ions. So this is a nucleophile. It will move its electrons to this carbonyl center, causing these pi bonds to break. So in the intermediate step, we are going to get this intermediate. And we have this OH here. But the next step is the protonation or the acidic workup. So this will use its lone pairs to pick this proton, causing these electrons to be moved to the oxygen and leading us to the final product. The final reaction we are going to talk about is the addition of an alcohol oxide. So let's assume we are given a cyclopentane carbaldehyde, and we are supposed to first add sodium methanoate, then the next part do the acidic workup. So this will lead us into this product. There is always one kind of product you are going to form, and it is this product. This is the nucleophilic part. Let's show it by reaction mechanism. It doesn't change. The mechanism is always the same. In solution, this will exist as the methanoate ion. So this is nucleophilic. It will move its lone pairs of electrons here, causing this bond to break. So we are going to get this intermediate in solution. The proton is here, and this is coming from the methanoate part. So the last part will be the protonation or the acidic workup. So this electrons, this will use this lone pairs to pick this proton, causing these electrons to be moved here and giving us our final product. So always, the most important thing is to identify the nucleophile. And we know that always you form an OH here, and then you add the nucleophile to it. We have a cyclohexanone. The first part is KCN in H3O plus. So you see that this is addition of the cyanide ion. So we are just going to draw back our cyclohexane, but we know that at the carbon bearing the double bond, we will form an OH, and then we will add the nucleophile, and the nucleophile in this case is the cyanide. So this is what we are going to form in this part, and in this part is the same thing. So draw our cyclohexane, we will form an OH here. Now the nucleophile here is the methanoate ion, so we are going to add a methanoate here, and this is sodium borohydride, so we will form an alcohol. So we'll draw our sodium hexane here. There's an alcohol here. There's going to be a proton here, and this is a Grignard reagent. So first we'll draw our cyclohexane here. We are going to have an OH here, and then this part is from the Grignard reagent. So this is what we are going to form in solution.